So what you see here are examples of refraction in a daily life. So in the first case, like it's obvious what is happening. It's a pencil partially dipped in water. The upper side of the pencil, the upper half, it's in air. The lower half is in water. And we, the observer, we are in air. So when we look at the pencil, it doesn't, like you can see how it appears. Now, at the beginning of this chapter, we discussed our eye perceives the presence of an object in front of us depending on how the light enters into our eye from that object. Okay, now it's a proper pencil, it's a straight pencil only, but when it is half dipped in water, it appears like this. So basically what happens, the pencil that must have been like this, you mark a point on it, let's say a red dot. Had there been no water, light from the red dot would have entered into our eye as if it was coming from that position where I'm showing it. But because of water, what happens? Or because of light traveling from water into air, what happens? Light bends and it appears to be coming from this point. It is actually present at A, but for us it appears to be present at B. Okay, so this is the effect of refraction of light. And in the second case, can anyone describe what is happening? Rishi, what is happening in the second case due to the water droplets? I know there is a reflection there seen on the water drops. Leave reflection. What else is happening? Yeah.
The smaller holes in the sheet are bigger. They seem bigger.
Texture, whatever is there, it appears to be enlarged. Okay. And see, it's a half water drop. Okay. Water drop on a tissue paper or something. Okay. Tissue paper will absorb it. Maybe this is a plastic sheet or something. There's a water drop on it, but it's not full. It's a hemispherical water drop and it appears to be enlarged. Okay. Third case, what is happening? Third case, it's a full glass sphere. Fine. There's an object, the mountain or hill behind the glass sphere. Observer, we are on this side. And when light from the mountain passes through the glass sphere, it somehow enters into our eyes, making us feel that the mountain is inverted. Okay, again, that is also bending of light only. And these are all effects of refraction of light. Okay. So can one of you quickly tell me what refraction means? What is the meaning of refraction? Okay. Refraction is nothing but change in the direction of a wave when it enters from one medium into another medium. Okay. When it comes to refraction of light, we say it is the bending of light when it travels from one medium to another medium. Okay. Now, why exactly refraction happens? You will learn in the next chapter. Okay. It's based on Huygens principle and all, Huygens wave theory. Let's say this is a ray of light incident on an interface. Interface is nothing but a common surface for two different media. Okay. Let's say the upper side of this is air. Upper side of this interface is air. And the lower side of this interface is water. Air and water are both media which allow light to pass through them. So when light is incident like this at an angle, you will notice that light does not travel in the same direction along which it is incident. It bends. Okay. And when it travels from air into water, the light ray actually bends towards the normal. It is observed like this in daily life. Okay. Now we know light is a wave. It's an electromagnetic wave, right? One of you tell me, what changes for a wave when it goes from one medium to another medium?
Sir, the speed.
Speed changes, and corresponding to that, the wavelength will also change. What remains constant is the frequency. Okay. So in air, light travels at one speed. In water, it will travel at another speed. Not just light. This is true for any kind of wave in general. When medium changes, the properties change, so the speed will change. And that is the reason why the ray bends. Okay. change in speed is the reason for bending of light when it travels from one medium to another. Okay, you can fine. In proper detail, we'll derive in the next chapter itself. Using Huygens wave theory, we can prove all this. So, yeah, how much the light bends when it travels from one medium to another depends on the difference between the two media. And what kind of difference are we talking about? We are talking about the difference between their refractive indices. So for any medium which allows light to pass through it, we can define something called a refractive index, okay, denoted by the symbol mu. Can one of you tell me the formula for refractive index of a medium in terms of speed of light? Okay, Pradhin has given the answer. It is the speed of light in vacuum, that is c, divided by the speed of light in that medium, v. Now, in vacuum, light travels the fastest compared to any other medium. Therefore, generally, c greater than or equal to v. That means c by v will be greater than or equal to 1. Therefore, the refractive index of a medium will be greater than or equal to 1 always. It will never be less than 1. Okay. And for air, refractive index of air, we take it as same as that of vacuum, 1. Okay, because in vacuum, the speed of light itself becomes c. C by c becomes 1. Okay, so these are simple things only. And for water, the refractive index is about 4 by 3, close to this value. And refractive index of glass is approximately 3 by 2, that is 1.5. Okay. And based on refractive index, you can tell the speed of light in that medium. Yes, by simple application of this formula. Because c is a universal constant, 3 into 10 power 8 meters per second. So if you know the refractive index, you can tell how much is the speed of light. Or you can do the reverse also. If you know the speed of light, you can tell how much is the refractive index. Okay, so remember, refractive index is a property of a medium. Okay, speed of wave is also a property of the medium itself. Therefore, refractive index and speed are related to each other. They are dependent on the medium through which the light is traveling. Fine. Now, it has been observed experimentally that when light travels from a medium of less refractive index, okay, like air refractive index is 1, I'll mention it here, to water refractive index is 4 by 3, that is 1.33. When light travels from a medium of less refractive index to a medium of greater refractive index, it is found to bend towards the normal. Instead of going straight, it bends towards the normal. And among two media, the one which has lesser refractive index is called the rarer medium. The one which has higher refractive index is called the denser medium. Now, when will refractive index be more? When the speed of light is less in that medium. Okay. So basically, in the denser medium, light travels slower. And in the rarer medium, light travels faster. Fine. So when it enters from rarer to denser medium, it is found to bend towards the normal. When the reverse happens, when it goes from denser to rarer medium, it bends away from the normal. Okay, you can just consider this itself in reverse direction. Yeah, come on. Suppose this is the incident ray, then this will be the refracted ray when it enters from denser medium to a rarer medium, like from water into air or something like that. So let me summarize that here. This is easy only actually. Rarer to denser the light ray bends towards the normal. See, this is very important because this helps you draw the ray diagrams in case of refraction. Okay. And next case, when it goes from a denser medium to a rarer medium, the light ray bends away from the normal. Okay. So the ray which enters into the second medium is called the refracted ray. Now, generally, for any kind of wave, be it an electromagnetic wave like light or a mechanical wave like sound, when the wave is incident from one medium onto another medium, reflection and refraction will both happen. All the energy won't get refracted, all the energy won't get reflected also. This is true for any kind of wave. But we have already studied the properties of reflection. How much energy gets reflected is not part of the syllabus now. Okay. But when it is reflected, how it gets reflected, we know at what angle, what kind of image it forms, all that we have discussed already. Now we are talking about the refracted part of the energy, refracted part of light. Reflection will also happen. Okay, don't forget that. Fine. Now, the relation between the angle of incidence and the angle of refraction. What is angle of refraction? The angle between the refracted ray and the normal. Okay, the relation between these two is given by Snell's law. There is proof for Snell's law that we'll discuss in the next chapter. Can one of you quickly tell me the formula for Snell's law? Isha, what is the formula for Snell's law? Rishi?
So
mu1
is it
Rishi, tell.
sin I by sin R?
See, sin I by sin R is not a formula. Formula will have a left-hand side and a right-hand side. Isha, you are saying something? Mu1?
mu1 by sin A is equals to mu2 sin R.
Mu1 sin I.
Sin A is equals to mu2 sin R.
Okay. You can write it as sin I by sin R is equal to mu2 by mu1 also. But most important, what is mu1 and what is mu2? Mu1, mu obviously stands for refractive index. It's the refractive index of the medium in which the incident ray is traveling. Okay, this is very important. Like if you don't know that, then you'll not know which mu to substitute. Okay, so this is mu of the medium of incident ray. That means the medium in which the incident ray is traveling. And mu2 is the refractive index of the medium in which refracted ray is traveling. Okay, all the formulas that we are going to discuss based on this also, or that we are going to derive based on this, will also stand true with this assumption only. Okay, will also be valid with this assumption only. One is for the medium in which the incident ray is passing. Two is for the medium in which the refracted ray is passing. Okay. We can also write it this way, sin I by sin R is equal to mu2 by mu1. Refractive index of second medium divided by refractive index of first medium. This is also called relative refractive index. Okay, refractive index of one medium compared to another medium, and it is denoted by the symbol mu21. Mu21 is mu2 by mu1. Mu12 will be mu1 by mu2. Okay. Anyway, these days in exams, they don't give you relative refractive index, they give you the actual value only. So you can clearly understand which is mu1, which is mu2, and which how they have to be divided. Fine. So when light enters from one medium to another medium, it bends. Now see, in all these, not all these cases, in the first two cases, light first travels through water, then enters into our air light first travels through water in the first two cases, then enters into air, and then enters into our eye. So light is traveling from water to air, and there is also light directly coming from air into our eye, traveling through air into our eye. Okay. So this upper part, the light coming from this enters into our eye directly. Even here, the light coming from here enters into our eyes directly through air. It doesn't bend anywhere. Okay. But the light coming from the lower part, this one, and here also, the part of the texture that is below water, it first travels through water and then enters into our eye through air. Okay. So that light is undergoing refraction, and when light undergoes refraction, the images appear different compared to the object. Okay. So we need to know what kind of image will be formed. In some cases, as you can see, the third example, the image is inverted compared to the object. We need to understand why all that happens. And I think in the third case, it also seems as if the image is formed very close compared to the object, the actual mountain. Its image appears closer. You may have observed this also. If you take a glass slab or a transparent plastic scale, okay, you put it on letters on a sheet of paper, the letters will appear to rise up, means the image appears closer than the object. Okay, all these are effects of refraction. So we need to know, due to refraction, where the image of an object will be formed, what kind of image will be formed and all. Okay. For that, we will derive a formula. We will derive a relation between object distance and image distance in case of refraction. Okay. So let's consider a spherical surface. The result we derive for spherical surface can be applied to a flat surface also. The radius of curvature of a flat surface is infinite. That's all. So in the spherical surface formula, you make the radius tend to infinity, you will get the result for a flat surface. Consider something like this. The ray diagrams, the approximations, those are all very important. So suppose there is an interface like this separating two media. Assume the left side is air and right side is all water. Fine. Somehow we have made a boundary which is shaped like this. Like you can take a water bottle, for example. Inside the bottle is water, outside is air, and it has a curved surface. That curvature is along, what can I say, only one axis. A sphere is curvature along two axes. Okay. Anyway, let's say there's a curved surface like this with one medium on one side. Let's call this refractive index as mu1. Some other medium on the other side, let's call it as mu2. Okay, actually it would have been better if I shaded the other side with some color, but let's not waste time on that. Imagine an object is placed somewhere here. I'm considering a point object. Oh, we need to find out where the image forms due to refraction, not reflection. Due to reflection, we know a convex mirror, we have discussed those cases. We know what happens due to reflection. Let's see what happens due to refraction. Now, Snell's law, mu1 sin I is equal to mu2 sin R. One of you tell me, if a ray is incident along the normal, okay, ray is incident along the normal, how much is the angle of incidence?
0, sir.
Angle of refraction then will be how much?
0.
0. If left hand side is 0, right hand side has to be 0. Now mu2 cannot be 0, so sin R has to be 0. And sin of what angle is 0? 0. That means if a ray is incident along the normal, it passes from one medium to another medium without bending. It will continue along the normal itself on the other side or in the other medium. We can make use of that here. Now to locate the image, we need to find out where the refracted rays meet. Okay, so we'll consider a few incident rays. We will draw their refracted rays, corresponding refracted rays, and see where they meet. Okay, so for convenience, one incident ray can be taken like this. Now it strikes the surface normal to it. Okay, means it's traveling along the normal. Angle of incidence is 0. Angle of refraction also must be 0. It continues straight. This is a very easy ray to trace. For the spherical surface, let's say this is the center of curvature. Randomly, I'm taking. Next, if you consider another incident ray from the object, maybe somewhat like this. Okay, let's call this first point as P. This second point of incidence, second ray's point of incidence as A. Ray was traveling like this. Now this ray is entering from air into water. That is just an assumption that I have made. I have assumed that mu1 is more than mu2. Sorry, mu2 is more than mu1. Okay, water is the denser medium. One of you quickly tell me, when light enters from rarer to denser medium, how should it bend?
Towards the normal, sir.
Towards the normal. So we'll draw the normal first so that we'll be able to draw the refracted ray properly. Line joining the center to any point on the surface of a sphere becomes a normal automatically. Now this ray, the second ray OA, it was traveling in this direction or along this direction. But it has to bend towards the normal now. Now bending towards the normal can happen in many ways. This is one possibility. It has bent towards the normal, but it's still going away from the principal axis. That is possible. Okay, this is where refraction gets tricky actually. Multiple possibilities will arise. Now, if it bends sufficient enough, it may even go parallel to the principal axis like this. That is also possible. And if it bends more than that, it will meet. I mean, after bending, the light ray will travel forward and meet the principal axis somewhere ahead here. So there are many possible cases of image formation. Now, what exactly will happen, we don't know. It depends on the refractive index. It depends on how much the light bends, right? For convenience, for deriving the formula now, let's assume the third case is what happens. The ray has bent sufficiently enough to meet the other ray on the principal axis. Okay. And wherever the refracted rays meet, that is what we call as the image location. If there's an observer on that side, the light will enter into the eye of the observer as if it is coming from the point I. Okay, there are a lot of things to be kept in mind here. If the observer is standing somewhere here, like, okay, if the observer's eye is somewhere here, the observer won't even see a clear image. If the observer is on this side, then there's a chance that the observer sees a clear image. It's also possible that the observer still doesn't see a clear image. Okay, we'll discuss all that when we talk about something called, what is that? Nearest distance or shortest distance of distinct vision. Okay, in this chapter itself, when we discuss about the human eye, we're going to discuss that point. Then you'll understand why some images can be seen clearly, some cannot be seen. Image will form, but whether you will be able to see it or not depends on where you stand. Okay, we'll discuss all that. Now, what our aim here is that we need to derive a relation between object distance, OP, image distance, PI. Of course, it depends on the radius of curvature and also depends on refractive index of the first medium and the second medium. It depends on mu1, mu2 and R, the relation between object distance and image distance. Because we need to know how much the light ray bends. How much the light ray bends depends on mu1, mu2. And the normal you see, it depends on the radius of curvature. So how much the light ray bends depends on the radius also. Okay. Now in this diagram, if you can visualize, this is the angle of incidence. I'll show it in yellow. This is the angle of incidence. This is the angle of refraction, R. Those two are related by Snell's law. Okay. Let's consider the other angles. Call this angle as alpha, this one as beta, this one as gamma. Okay. One of you tell me, while deriving the mirror formula, we made an approximation or an assumption. What was that? While deriving the mirror formula, we made an assumption. What was that? Or under which condition is the mirror formula applicable, valid? Okay, you need to practice derivations. Okay, don't just listen and leave it off. You have to know how every formula in your syllabus is derived. Okay, now the approximation or the assumption we make while deriving the mirror formula, or even in this case, is that the point A is very close to P. If A is very close to P, AP becomes perpendicular to OP. Whatever we derive is based on this assumption. Okay, and for A to be very close to P, the angle alpha will have to be a small angle. The ray OA will have to be very close to the principal axis. Such rays are called paraxial rays. Okay, whatever result we are going to derive, whatever formula we are going to derive now is also valid only for paraxial rays, only for image formation by paraxial rays. Paraxial means rays which are very close to the principal axis. Here in this diagram, I have shown OA deviating significantly away from the principal axis, but that is shown like that for our convenience. You imagine A very close to P, then AP will almost be a straight line perpendicular to OP. Okay, keep this assumption in mind. So paraxial rays. Only images formed by these rays can be found using this formula that we are going to derive. Same applies to mirror formula also. Fine. So as I said, what is our aim? To relate object distance, image distance, and the radius. So we have to relate OP, PC, and PI. Again, we'll make use of properties of triangles. What else can we do? If you can find a relation between alpha, beta, and gamma, then you can relate OP, PC, and PI. Can any of you tell me how alpha, beta, gamma can be related? Okay, first consider the triangle OAC. See, if my teacher had asked me how they can be related, I too probably would not have answered if it was the first time. But I've done it many times, so I know how it is done. But you can take a hint from what we discussed in the like what we used while deriving the mirror formula. While deriving mirror formula, we use the idea that external angle of a triangle is equal to the sum of internal opposite angles. Here also we use the same idea. For the triangle OAC, okay, I is an external angle of incidence. One of you tell me, what are the internal opposite angles to I in the triangle OAC? External angle is I. What are the internal opposite angles? Alpha and beta. Okay. So I is equal to alpha plus beta. First equation. Next. Okay, we got some relation involving alpha and beta. Now we need to bring gamma also into the equation somehow. So now look at the other triangle ACI. Isha, tell me in the given diagram, for the triangle ACI, which is the external angle? Which angle is outside the triangle? Rishi, can you tell which is the external angle for the triangle ACI?
Alpha, sir.
Alpha is not nowhere near the triangle ACI. ACI is this.
Oh, beta then.
Beta is the external angle and the internal opposite angles are gamma and R. So we can write beta is equal to gamma plus R. That's the second equation. Okay. Now in reflection, we knew I is equal to R. Angle of incidence is equal to angle of reflection. But this is refraction of light, bending of light. Okay, when it goes from one medium to another. And I and R are related by Snell's law. So from Snell's law, we know sin I, okay, mu1 sin I is equal to mu2 sin R. Now if you substitute I as alpha plus beta here and all, it will become too complicated. But you observe the diagram, the ray diagram. I told you whatever we are going to derive will be true only for paraxial rays. Now if it's a paraxial ray, means all the rays are very close to principal axis. You have to imagine OA being very close to OP. If OA is very close to OP, alpha becomes a small angle. And if alpha is a small angle, automatically I will also be a small angle. R will also be a small angle. Beta, gamma, all of them will be small angles. Okay, if the point A comes very close to P. So for paraxial rays, alpha, beta, gamma, I and R will all be small angles. And can one of you tell me, for small angles, what is sin x approximately equal to? Suppose x is a small angle, what is sin x approximately equal to? Or you must have studied something like this. Limit x tends to 0, sin x by x. What is this equal to? Okay, revise
Where
11th
it
class.
tends to 1.
The limit tends to 1. Sin x by x tends to 1 means sin x tends to become equal to x. Okay. So for small angles, sin x is approximately equal to x and it is also approximately equal to tan x. You can substitute and check if you want. You can use a scientific calculator or Google. Take very, very small angles, sin x value, tan x value, and x value will almost be the same. Can any of you tell me up to what angle this is valid? Well, like what kind of angles are small angles? Or what range of angles can be called small angles? Okay. In degrees, it is valid up to 5 degrees. Any angle less than 5 degrees will be considered a small angle. But you can't substitute the angle in degrees in this formula. You can't write sine 3 degrees is equal to 3. That is meaningless. Sine of no angle will ever be more than 1. Okay. In degrees, the angle can be up to 5 degrees. But when you substitute it in this formula, you have to substitute in radians. So remember, for small angles in radians, sin x is approximately equal to tan x, approximately equal to the angle in radians itself. Okay, I'll write it here, x in radians. These are all mathematical things you should be knowing. Okay, anyway. We are going to use that here. Now, according to Snell's law, mu1 sin I is equal to mu2 sin R. And for paraxial rays, I and R will be very small angles. If I and R are small angles, you can write mu1 into I is equal to mu2 into R. We can write it like this. Now from the first equation, I is alpha plus beta. Therefore, mu1 into alpha plus beta is equal to mu2 into, from the second equation, R is beta minus gamma. So beta minus gamma. Okay, now we got a relation between alpha, beta and gamma. If you can relate alpha, beta, gamma, you can relate the sides OP, PC and PI. The same way we did it while deriving the mirror formula. We use tan alpha, tan beta, tan gamma. One of you look at the triangles and tell me how much is tan alpha? Or how do you express tan alpha?
So it'll be AP by OP.
AP by OP. Correct. Tan beta.
AP by CP.
AP by, we'll call it PC. Actually, this also should be called PO because all distances are to be measured from the pole according to sign convention, which we will apply. And tan gamma will be AP divided by PI. Okay. And these are also small angles only, alpha, beta, and gamma. And for small angles, tan of the angle is equal to the angle itself when the angle is taken in radians. So in place of tan alpha, we'll write alpha as AP by PO. In place of tan beta, we'll take beta itself is equal to AP by PC and so on. Therefore, we can write mu1 into alpha was AP by PO, beta was AP by PC. Beta is up to center only, no? Yeah. Is equal to mu2 into beta AP by PC minus gamma is AP by PI all the way to the image. Fine, AP gets cancelled. And we would like to derive a formula which is applicable along with sign convention. Till now, we have only used trigonometry. And in trigonometry, like sides of a triangle are always taken positive. But we want a formula which is applicable with sign convention. Now, if you apply sign convention, PO, the distance PO is actually negative of the object distance. See, rays are going to the right side. Rays are going to the right side, then anything on the right will be considered positive. Anything to the left is considered negative. So the object distance here is supposed to be negative. Okay. So you can say that object distance U is negative of PO or PO is negative of U. You can say like that. Next, radius is from P to C. In this diagram, center is on the right side. So radius will be taken positive as it is, we'll substitute. Next, P to I is the image distance and I is on the positive side only. So PI itself will be the image distance. So we'll keep VI as P. Sorry, we'll keep PI as V, PC as R, but PO will be substituted as minus U. If you do that, you get mu1 by PO is minus U plus again mu1 by PC is radius R is equal to mu2 by PC is the radius R minus mu2 by PI is the image distance V. We'll keep it as it is. Send the mu2 by V term this side. You get mu2 by V minus mu1 by U is equal to mu2. This mu1 will go to the other side, become minus, and you get mu2 minus mu1 by R. This is the formula, or this is the relation between object distance and image distance due to image formation by a, or in case of image formation by a spherical refracting surface. So spherical surface refraction formula. And remember, as usual, mu1 is the refractive index of the medium in which the incident ray is traveling. Mu2 is the refractive index of the medium in which refracted ray is traveling. And this formula is valid when applied with sign convention or when applied following sign convention.